This is problem set number 6, problem 3. A tetrahedron is a pyramid made of 4 identical equilateral triangles. Suppose a charge Q naught is suspended inside the tetrahedron at the center. So Q naught is the same distance S from all 4 vertices of the tetrahedron. What is the electric flux through the bottom face of the tetrahedron? Hint: if you find yourself grinding through lots of math, you've missed a shortcut. Okay, so I drew a picture of our problem. We've got a tetrahedron here, right, where all sides are equal length. This side, this side, this side, and that side, they're all equal length. We've got 4 faces: face 1, face 2, face 3, and the base, face 4. Okay. Inside this tetrahedron, right in the center, we have this charge Q naught suspended inside, and it is equidistant from all 4 vertices of the tetrahedron, 1, 2, 3, 4. Or in other words, it's the same distance from all 4 faces of the tetrahedron. Okay. What is the electric flux through the bottom face of the tetrahedron? Okay, so we're going to use our electric flux formula. It's electric flux through any Gaussian surface is equal to the surface integral of the electric field times dA, which is also equal to Q, the charge enclosed, Q enclosed, over the constant epsilon naught. Okay. So this is the electric flux through any Gaussian surface, which is what we're looking for. And we're going to use this formula to find that. This is the charge enclosed inside the Gaussian surface, which in this case is Q naught, right in the center. And this is the permittivity of free space, which is just a constant. Okay. What else? The point charge inside this Q naught in the middle of the tetrahedron has an electric field that points out radially in all directions. So because it's equidistant from all 4 vertices, it's gonna have an equal distribution among each face. So among all 4 faces, we'll have the same equal distribution, because this is kind of what that looks like, right? This is the point charge in the middle, right here, this ball. And the electric field is represented by these spikes. It comes out radially from this point charge. So it's going to hit all 4 surfaces of this tetrahedron equally. Okay. So let's plug in what we know. So this is the electric flux through all 4 surfaces of the tetrahedron. So that's total. Or actually, I'll put rather than total. It is a total, but I'll say that's the electric flux for 4 surfaces of the tetrahedron, okay? And that's going to be equal to the Q enclosed, charge enclosed, divided by the constant epsilon naught. And as given in our problem, the charge enclosed is Q naught, okay? So this becomes Q naught divided by epsilon naught, okay? So this is, again, the total electric flux through all 4 surfaces of the tetrahedron right here. Surface 1. This is surface 2. This is surface 3. And then we also have a base, right, which is surface 4. Okay. So since the point charge of the since the point charge's electric field goes out radially in all directions, and the point charge is located at the center of the tetrahedron as stated in the problem, the total electric flux right here is going to be equally distributed among each phase. So again, for all four surfaces, this is distributed equally among all four surfaces. Therefore, if we just want to, because all four surfaces receive the same portion of the total electric flux, if we are looking for the electric flux through the bottom face of the tetrahedron, right, then I could just take this and divide it by 4, right? So therefore the electric flux through the bottom face of the tetrahedron, bottom face only, is going to be equal to the total electric flux on all four surfaces divided by 4, right? Because there's 4 surfaces on the tetrahedron. So that's going to be Q naught over epsilon naught, which is a total electric flux through all 4 surfaces divided by 4. So our final answer will be Q naught over 4 epsilon naught. Okay, and that's the electric flux through the bottom surface. Bottom surface, or bottom face. And that's the final answer for this problem.